All right, so question 31. Marcela, if you're Spanish. Well, but it's got two L's, so it's Marcella. She's Italian. All right. Marcella gives her baby sister a ride in a cart. She pushes the cart steadily along the length of a horizontal driveway. And there's this little younger brother there, right? And there's the little Marcella clan and their little spider child in the cart. So, starting from rest, the cart at the end of 4 meters ends up with a speed of 2 meters per second. So let's kind of talk about what's going on here. Whenever I push something over a distance and I get a speed from rest, I always want to go with this equation as my starting. And u in this case is 0. So let's just see what we can do. So first of all, I know that I end up with a speed of 2 meters per second. My initial speed is 0 plus 2 times a times a distance, which is 4. So I'm getting an acceleration of 1/2 meters per second squared when her mom pushes. Now her brother pushes the cart with only half as much force. That means the acceleration that the brother imparts is going to be half as much, which is 1/4 meters per second squared. And we want to know how much distance the younger brother is going to need to push the cart. So, in order to get a speed of 2. So for the brother, so this is the first part that I did. For the second part, let's do it over here. V squared is u squared plus 2a of the brother times s. So 2 squared is 0 squared plus 2 times 1/4 times s, which is what we're going to solve for. So I've got 4 equals 1/2 times s. And I'm getting s is, in fact, 8 meters of distance. Awesome. So that's kind of how we compare things. Okay. So there's always a before and after with problems like this that we compare. Now for 32, it's a little deceptive. We want to know, so we've got PV over T equals a constant. Now first let's look at the choices because it looks like we're doing some kind of a graph. So we've got P's and V's here. So let me first of all just try to figure out what the relation between P and V is. So I've got PV over T as a constant that I'll just call C. Now P over T equals C divided by V. So what's going to give me a linear graph? P could be my y-axis. And then it looks like if I plot P versus 1 over V, then I'll get a straight line looking at the form of the function. This one, memorize. The units of gravitational field strength are newtons per kilogram. By the way, let's be clear. On Earth, G is 10 newtons per kilogram, which is the same as 10 meters per second squared. But when we're referring to it as gravitational field strength, we don't mean the acceleration. It is the same as the acceleration of falling. But we're going to distinguish it with these units just for context to let us know we're talking about the strength of the gravity field, not about its ability to accelerate objects. All right, 34. A projectile is launched horizontally from a high tower. We want to know what represents the vertical component of the velocity. So if we're looking at the vertical component, it starts with a vertical speed of 0 and then gets faster and faster going this way, so it's c. Now, if we asked you for, so this is the vertical, right? If we asked you for the horizontal velocity versus time, okay, that would actually be a flat line like this that never changes, just to be clear, for horizontal. Now for 35. An astronaut drops an apple on the surface of the moon with the acceleration due to gravity is 1/6 that of Earth. We want to compare the time to fall on the moon versus Earth. So let's do a little calculation. Whenever I'm doing falling questions, I have S is 1/2 AT squared plus UT. U is going to be 0, so I've got S on Earth is 1/2 GT squared. So 2s over g under a square root, okay, is the time on Earth. Now, you know what? I don't even need to make it s on Earth. What I should say is this. S is 1/2 gt squared. Sorry about that. The time on Earth is what we're solving for. So we got 2s over g under a square root. That's the time on Earth. Let's compare that to the time on the moon. Same height. Initial speed is also 0. So I've got g of the moon times t squared. T on the moon squared. So I'm going to get 2s over g on the moon is t on the moon. Now, it's 1/6 that of Earth, so this is going to be 2s g over 6. Now, the way fractions work, this goes on top, so I'm going to get 6 times 2s all over g. So when I compare t Earth to t moon, I'm seeing that it takes radical 6 times as long to fall on the moon as it does on the Earth. All right, 2 people are pulling on the rope with 100 newtons of force. What's the tension in the rope? This is a weird question. The net force on the rope is 0, but let's be clear. In other words, the rope pulls on this person with 100 newtons and this person with 100 newtons. So I read 100 newtons here and 100 newtons here that cancels, but when I actually hook up a spring scale, I'm going to read 100 newtons of tension, even though it cancels throughout the rope. It's a very weird question. So, number 37. Maria pushes a book against the ceiling of her room. The book weighs 20 newtons, and she pushes upward with a force of 25 newtons. So let's just look at a free body diagram for the book. So first, I've got the force on the book from her hand. Then I've got the weight of the book. Lastly, I've got a downward force, the force on the book from the ceiling. So let's add all these up. The book hand force, we're told, is 25. The weight of the book is 20. To balance, this has to be 5. So let's see what choices we have. So ceiling and book, 5 newtons. Book in her hand, 25 newtons. So that gives us choice B in order to balance the forces with the book. 38. Liam is pushing a box up a ramp at constant speed. What does this mean? No kinetic energy gained. And we're pushing it up a ramp, so there is PE gained. There is friction between the ramp and the box. The box is gaining potential energy. Not gaining kinetic energy. Not losing kinetic energy because its speed stays the same, so we're left with choice C. Only gaining potential energy. And then we have young Anna riding a bicycle at a certain speed. She stops pedaling, slows down to half her speed, and we want to compare the kinetic energy. So let's be clear. By the way, just a general rule, okay? There's kind of a squared relation between speed and energy. So if you have half the speed, that's going to be 1/4 the kinetic energy. 1/3 the speed gives you 1/9, etc. Let me show you. Here's how. So original kinetic energy, 1/2 mv squared. New kinetic energy is 1/2 mv over 2 squared, which is 1/2 mv squared over 4, which is 1/4 k0. And that's how I'm getting choice B. All right, number 40. A child slides down from the top of each of 3 slides as shown. All the slides start and finish at the same height above ground level and can be taken as frictionless. Once again, IB is repeating itself. Don't let this trick you. Beginning and ending height is all that matters. We did that in a previous video. So the answer is D. All 3 slides give us the same speed at the bottom. So that's questions 31 through 40.